Okay, it's getting brighter. All right. So welcome back, week 9. Good news. I've got good news and bad news. Who wants the good news first? Who wants the bad news first? Okay, I'll do the good news first. Actually, it's the same news. We're halfway through the semester. So it's good news if you're liking the class. It's bad news if you're not liking the class. Okay. But just a little reminder, we're actually a little bit more than halfway because we have one more holiday session. One of the coming Mondays is going to be a holiday again. I think it's week 17. Is it? Maybe? Okay, all right. So it's actually we're more than halfway through because we're going to be missing a class. Okay. All right. Today I want to wrap up what we were talking about last week, show you one or two things more, and just kind of talk about, just kind of recap what we've done the past about 7 or 8 weeks, kind of like this section on testing and things and inference. All right, so let's jump into it. All right, so I had a homework for you guys, and I think it wasn't too bad, but maybe you're getting used to it. Maybe you're not getting used to it. I don't know. Let's take a look, okay? So I just want to kind of go back over this little assignment that we did about this little experiments where we have different types of media, um, where some people were exposed to a video, some people were exposed to like a still video, some people were exposed to text and images. Some people were only exposed to text, okay? Out of curiosity, how many of you actually watched the video? Okay, a few of you actually watched the video that was linked, okay. All right. So this was a little experiment, and let's kind of see like what this is about. So let's first load the data up, okay? So every week I'm kind of throwing the data to you in a slightly different format, so you just kind of get used to handling data coming at you with different types and styles, and sometimes you have to put it together in strange and interesting ways. So this time there were 4 files I sent the data to you with, um, and uh, I asked you to kind of just put it together in something like this. All right, just to kind of, so you could just stick them together one row below the other using rbind, this function that I think I covered a little bit in class last week. All right. So what does this look like? Let's just take a look at the first few rows. And you see that the data looks something like this. It apparently the data already has some value called media associated with it that already tells you if it was like which of the 4 treatments the respondents were subject to, right? Um, and then there was one variable, I think it was intent 0. Was that the one that I asked you to kind of like use as the response variable, as the kind of outcome variable? Okay. And there's some other variables in here. We're not really using all of it. Okay. So if you put it together, then we will have this data set where the media values tells us which of the 4 treatments was the respondents were subject to. All right. All right, great. And so let's take a look at what this data looks like. So first of all, the response variable we were interested in was this one, right? And if you look at that data before you start actually putting it into models and things, you'll notice that it's maybe a little bit different than the data that we've seen before, all right? First of all, it's on a 7-point scale, and there's no fractional values in the middle, okay? So technically, it actually is not a continuous variable at all. It's just like 1, 2, 3, 4, 5, 6, 7. There's no 1.1, 1.2, nothing like this, all right? And the appropriate way maybe to visualize it, perhaps, is, well, you could do a density diagram, a density plot, right? So plot density, and let's just Oops, excuse me. Let me just cut and paste that in here. And you might see something like this. All right. Though perhaps a more appropriate way to model this might be to use a histogram, okay, with 7 breaks, because there's literally 7 different scores that are possible. And we see roughly a similar figure, all right? So this is what the data looks like. And of course, this is the full data set. There are 4 different samples that have come together to form this, all right? So we might be a little bit curious about what these 4 different data sets look like. And there's a few ways to go about doing it. First of all, let me look at some descriptive variables, okay? So one thing I'm going to do is I'm going to try to look at the mean of the 4 different samples, and there's a few ways of doing it. I could look at these media 1, media 2, media 3, media 1, 2, 3, 4, at these 4 different media variables separately and ask for their means. Or else, since I put them together already in that experiment data set, I could just take a look at them within the experiment data set, like within the full data set where we bound them together row-wise, okay? However, however, this is all the different medias together, but maybe I want to take a look at the mean of each sample individually, all right? But I've already put them together, so how can I break them up so that I can look at their means separately again? So as I mentioned, one way is they're already broken up with media 1, 2, 3, 4. I could look at it that way. But another way is this. I could take this variable intent 0 and split it up by the different medias that it belongs to. And there's a command called split that does just that. All right. So by themselves, intent 0 looks like this. Experiment media looks like this. And what I would like to get is this data split up by these variables. All right. And there's this little split command that does it for me. And let's just take a look at what that gives me. So I'm going to say split this variable by this variable. And this gives me a list. This is a list, and I can see that it's a list by just calling class on whatever that is. It's a list, okay? Where every element of the list is the first variable, the intent variable, and the list is broken into 4 elements corresponding to the 4 different types of media, okay? So just one more function in your arsenal of things that you know is that you can actually split a variable according to a separate criteria, all right? Why would I want to do that? Because once I have a list, I can do stuff like this. I can apply functions to a list. So in this case, all right, I'm applying the mean function to this list of intent variables split by the media. And that gives me 4 different means, one for each type of media. All right. So that's just one way that I'm going to use to try to describe the variables for myself as a central tendency, the mean. All right. There's many ways to do this. I'm curious how if you were looking at the descriptives. Did I ask you to look at the descriptives? Was that part of the homework assignments? Not necessarily. Yes, no? Anybody remember? No, okay. All right. Well, if you did, this would be one way to do it. Okay. Um, all right. And then here I'm just rounding them off to kind of look at them reasonably. And okay, interesting. A lot of these 4 samples have fairly similar means, except one is a little bit off. All right. Okay. We'll come back and look at that later. We can also visualize this data set. So a few ways, and I left it up to you how you would like to visualize it. Okay, I didn't tell you this time you must visualize it this way or that way, but I'd like to see how you visualized it. And in the peer reviews, you will get to see how other people visualized it, at least how 2 other people visualized it. Okay. Um, so here's how I did it. Eventually, I want to do a box plots. Okay, so one way is just to do a box plots. The box plot is good interesting. It does show me that, there's one variable, there's one media type where the responses were a little bit lower than the others. All right. So that's nice. However, remember that I'm kind of interested not in the distribution of these 4 samples, but I'm more interested in comparing the means of the 4 samples. Okay. So I decided to do something a little bit different, which is the box plot gives me a sense of the distribution of the 4 samples, but I'm interested in where are their means. And one way to possibly visualize that is to look at the distribution of the means rather than the distribution of the whole data. Okay. So the way I did that, and this is just my own little weird way of doing it, but maybe you'll appreciate it, is first, and I'll kind of jump to the code here first. Okay. So first, I'm going to again split this variable by the media types and get its standard deviation this time and the length of each sample. All right, so that gives me the standard deviation of this intent variable across the 4 media types and the lengths as well. So let's take a look at what that produced. This media SD now is simply the 4 standard deviations. And the standard deviations are not altogether different. They're fairly similar. And then the length of the 4 media types. Oops, excuse me. And the length of the 4 media types. All right. From this, and I can just divide one by the other. I can divide the standard deviation of the 4 media types by the square root of their length to get the standard error, right? And this gives me the standard error of the 4 samples. Now, what is the standard error again? The way I like to think about it is the standard deviation of the mean. It tells me how much the mean of these 4 samples might deviate if I was to sample again and again. All right. So now what I can do is on top of these box plots that I've drawn, I can draw a line segment. Let me just show you what I'm drawing first, and then I'll explain what it is. Okay. So what I've shown here is these blue line segments that you're seeing here is the roughly 95% confidence interval of the mean of each of these 4 samples. All right. So the box plot allows me to see the the distribution of the 4 samples. And these little blue line segments that I've drawn allows me to see the distribution of the mean, the 95% confidence interval of the mean of these samples. All right. And the reason I felt that was important for me, hold on, is the microphone turned on? Or maybe I forgot to turn it on. Can you hear me in the back, or is the microphone on? No, it's not on. But you can hear me still. Is that better? Better? Okay, all right. I'll turn the microphone on. All right, so what you can see now is that since ultimately I'm interested in comparing the means, this gives me a visualization of the means as well, not just of the data. All right. So that was just my way of kind of visualizing the data to see for myself what it looks like. All right. And just by eyeballing it, I would say that, media 1, 3, and 4, it would be almost impossible for any statistical algorithm to find a difference in their means, because you can see these blue line segments are almost identical. All right. But the second one, it's possible it's a little bit lower, and it's possible that it's a little bit different. All right. So that's just a little bit of that's how I'm kind of visualizing them. All right. So once again, I'm using the segments function that I discussed last time. And just a reminder how segments works. You can draw one or more lines, just lines on your plot using this segments function. All right. And it adds the segments to the existing plot. So you have to plot you have to make a plot, and then you can add these segments. All right. And what you've got to provide it is 4 different things. the starting x values, the starting y values, the ending x values, and the ending y values. And you can use this to draw the 4 line segments. So in my case, the starting x and the ending x values are the same. It's just, excuse me, I'm saying the x values are 1, 2, 3, and 4. All right. And each line segment is going to have the same starting x and ending x. It's going to be just for media 1, the starting and ending x values will be 1. For media 2, it'll be 2, 3, and 4. So as a result, the starting x and the ending x are just sequences of numbers 1 through 4. Okay. And then the starting y and the ending y will be the mean of each of these samples plus, well, minus and plus 1.96 times the standard error. Okay. And that draws for me altogether these 4 segments. All right. I suppose one thing I could add to improve this a little bit is I could also add some points. All right. And I think for points, I have to give x and y. So I could just put the means as well. So the x will be 1 through 4. The y will be, if I remember how to use points correctly, will be media mean. Okay. And I want to get a solid circle. This little PCH command in any of your scatter plots, anywhere you're drawing points, will tell R what kind of point you want. And I'll show you in a moment what that refers to. Okay. So I think if I do that, yeah, that's going to give me the 4 means as well. All right. So there I have it. I have 4 means and their confidence intervals, and also the box plot telling me the overall distribution of these samples. All right. Okay. Cool. So I'm curious, how many of you used a box plot to visualize this data to see what it looks like? Anybody? Oh, a lot of box plot fans. Great. How many of you used the density plots? How many of you use both? All right. Okay. Good. How many of you use something other than a box plot or okay, what did you use? What's that? Violin plots. Oh, excellent. I'll talk about that in just a second. Okay. All right, great. Anybody else using a different type of plots? Okay. Part of question 2 also asked if the assumptions of Anova are met in this case. And one way to kind of have a look at that is just using the QQ plots, again, the normal QQ plots. How many of you drew a normal QQ plot to see what this data looks like? Anybody? Oh, a few people. Okay, several people. All right. So you could also do a QQ plot to see if this intent variable is actually fairly normally distributed or not. Actually, you'd have to look at it for each of the samples, but I just did one overall. And if you do it, you'll see that it's a little bit harder to interpret this time because you get this, what we call a stepwise. It looks like steps, like going up the steps, right? Why? Because the data that we have is actually corresponds to 7 different levels. It is not a continuous variable. You can still use a normal QQ plot to kind of see if this is a fairly normal distribution or not, but it's a little bit harder when you have this kind of stepwise situation. All right. But overall, looking at this, I would say it does deviate a little bit from a normal distribution, at least down here a little bit. All right. Okay. So just some ways of kind of taking a look at this. I also drew some density plots of each of the 4 media, the intent variable of each of the 4 media types, to kind of take a look at what their distributions look like. And it's quite apparent that by and large, they're not very normal, even though that is one of the assumptions of Anova. All right. And yes, there are other ways of visualizing, doing the visualizations I just showed. One popular type of visualization is called a violin plot. It does not come with R. It comes in a little package called Violin Plot that you'd have to install. How many of you tried a violin plot? Anybody? You one person? What package did you use? Did you use this package or a different one? ggplot's own has its own violin, right? Plots. Okay. I'll talk about ggplot in a different week. All right. By the way, out of curiosity, how many of you are using the ggplot package to plot things? One person in this class? Okay, maybe I should introduce that sooner rather than later. Okay, you might like it. So I installed that Vioplot, and then I'm just gonna load it here. And what I can do with so I'm going to create what's called a violin plot. You'll see why it's called a violin plot perhaps in a second. So the way it works, well, let me just show it first on screen. It looks something like this. Okay. So violin plots, it's called a violin plot because it's got this curvy shape. It kind of sort of sometimes looks like a violin that you might play. All right. But it does two interesting things. It shows you both the density plot and the box plot at the same time. All right. So it shows you so what you see, the curve that you're kind of seeing here, it's a symmetric curve. It's showing you basically the density plots symmetrically. All right. And at the same time, it's showing you the box plots in the middle, but the box is kind of like a thick line segment instead of a box. All right. So this is another kind of plot where you're interested in viewing both um, the density function and the quantile description that the box plot provides at the same time. All right. So for those of you who are drawing box plots and violin plots, and I think there was about half a dozen of you, or about 6 or 7 of you in this class, at least of those attending, if you find yourself constantly drawing a density plot and a box plot in every single assignments, maybe you're a fan of the violin plot because it's doing both at the same time for you. All right, cool. So over here, I've kind of shown you how the violin plot looks like. And you can figure it out if you just look at the help function. So I'm using the library Violplot. There's other libraries that draw violin plots, but I'm showing you this one. And in here, you basically just show it, you tell it the 4 different response variables, and it'll draw 4 different plots for you, just as we've been doing. All right. You can do it horizontally or you can do it vertically. It's entirely up to you. All right, cool. So those were some visualizations to kind of see what it looks like. And again, once again, here we can see these don't seem to follow a very normal distribution. There might be one sample in here that follows a fairly normal distribution, perhaps, but the others might even be, one or two of them might even be bimodal to a certain degree. All right. Nonetheless, we can conduct our classical F-test to see what this looks like. Excuse me, a classical Anova. All right, and I'm using the one-way Anova test that we saw last week in class. And let me run that first. All right, and let me take a look at what that looks like. So let me actually just write it out here again. So, oops, it's a little bit hard to see. Okay. Move it a little bit forward. Does it resize? Okay. So what we're seeing here is basically I'm calling one-way test. And this is the model that I have in mind. I'll talk in a later week about what I mean by model. But for now, I just mentioned that when you're trying to do an ANOVA using something like one-way test, you just give it the dependent variable, the variable that you're kind of interested in seeing how it responds, and the variable that you think might be causing that response. In our case, it's media, all right? Once again, be careful to let R know that this media variable, even though it looks like numbers, 1, 2, 3, 4, it's actually a categorical variable. And you can tell it that with this factor command, okay? That forces R to consider this as a categorical variable, all right? It's up to you how you set this var equals, all right? Out of curiosity, how many of you said var equals true? How many of you said false? Just me? All right. Did the assignment tell you which way to do it? Maybe, maybe not. No, I don't think so. But it's up to you. And in this class, I'm not going to bother you too much about what your assumptions are. But when you're actually doing studies, this is where some expertise about the domain would come into play, where you would ask yourself, is there a reason to really believe that the variance would be different based on different media types? How would you know that? Maybe from experience. Okay. Maybe you would say, yeah, we know for a fact that when people read text, their responses are completely different than when they're looking at videos, and we expect a higher dispersion or something like this. All right. But I won't belabor you about your assumptions in this class, but depending on your actual experiments that you might be conducting, you'd want to think about that. Okay. Oops, why are there warnings? Okay, there are warnings because of the graphical stuff I did before. Right. And this gives me an F value, F statistic of 2.9, and a P value of about 0.03, which tells me that the results are significant at the 5% level, but maybe not at the 99% level. All right. And I'll talk about p-values and how meaningful they really are. You may have noticed that this semester I'm not really like forcing you to, well, I'm telling you at least try 95, 99. I'm not being very picky on which one. I don't seem very religious about it. And I'll tell you a little later about why I'm not being so picky about them. All right. Okay. All right. So that's that. And I can actually also take a look at the cutoffs of the of Anova of the F statistic using this QF function that I think we discussed earlier this in a week or two ago. Okay, here I'm asking what is the F values I would expect with these degrees of freedom. All right, for 95% and 99%. And that gives me my cutoff values of F, 2.66 and 3.9. You'll notice that our F value is bigger than the 95% cutoff and smaller than the 99% cutoff. All right. Okay. So that's kind of just a recap of Anova. And yes, we can bootstrap this thing. I think most of you had nearly identical functions to this. Did I provide the function, or did I ask you to? I asked you to write it yourself, right? So, so this is the way I did it, just to take a look at it briefly. All right. For the null and the alt, I have two different ways of setting them up. The alternative is always simple, because all you got to do is resample from the data that you're interested in, and then your alternative values are simply the resampled values. All right, the alternative values are always easy to do. Excuse me, the alternative values are the test you want to conduct on the resampled data. All right, so in this case, I simply use the alternative values. My model takes a look at how the treatment numbers affect them, and then I get the F statistic for it, okay? The null is a little bit different. For the null values, I am mean centering them to kind of simulate a world where they all have the same mean, all right? I'm basically simulating an experience where all the media types have the same mean. Why would they have the same mean? How would they have the same mean? Well, if I mean center each sample, then each of them has a mean roughly of 0, okay? However, because I am resampling, they will not have exactly a mean of 0. They'll have means close to 0 with some error associated with it. All right, and the resampling will kind of produce that error randomly by itself. All right, so that allows me to kind of create 4 samples which look like I'm just resampling, but the difference is that I'm resampling from mean-centered data. Okay, and it's important here that I am resampling after I've done the mean centering, not before. Because if I resample and then subtract a mean, I'm kind of giving them all exactly the same mean, which would not really happen in nature. All right. So that's my bootstrapping function. And now I can set a seed and replicate. You'll notice this takes quite a bit of time to replicate this, all right? Because there's 4 samples I'm having to resample. And I'm actually doing 8 resamplings and 2 F tests. So it takes a little bit of time for this to run, right? Once again, remember, you can choose how many times you want to replicate. It'll be pretty quick if you just do 500 or 10. Sorry, excuse me. These errors are not related to bootstrapping. They're related to the graphics because I have this image and R is trying to redraw it over and over again, and it's unable to do it, and so it keeps giving me errors. All right. Okay. I'm using about 10,000 here because it's a sizable number. It's not too small. The results do tend to stabilize around 10,000. All right. And nowadays, with the computing power of our laptops, 10,000 it takes a little bit of time, but it's enough time for you to go out, make some tea, and come back. Okay. It's not much more than that. All right. And I get my null values and my alternative values here. Okay. And I can plot these out. So let me plot the null values. You see what a nice F shape this has? This looks like a classical F distribution because it is a classical F distribution. I've simulated a very, very classical F distribution, which peaks close to 1, but not necessarily exactly at 1. Okay. And then I can plot the alternative distribution on top of this, and that is my alternative distribution. All right. You notice my alternative distribution is also an F distribution. These are both F distributions, but F distributions are a family of distributions. And the closer you are to the null assumption, the more it looks like the classical F shape. All right. And the more it strays from the null assumption that all the means are equal, the more that it's different from that assumption, the F distribution kind of changes its shape as it skews to the rights. All right. All right. And I'll show you again a little bit later this lecture why I'm so obsessed about both these distributions, right? Because and I have one more thing to show you basically. So let me also draw a line where these are the 2 vertical lines that correspond to the 95% and the 99% cutoff of the null distribution. Okay. And then I'm going to draw a vertical line where the actual F statistic of my original data was. And as you can see, it's um, I could potentially reject at 95%, but I can't really reject at 99%. All right. So that's roughly where my F statistic is. Um, and you might wonder, well, why did we have to compute this alternative value? We could have just looked at the null distribution and this F value and the 2 cutoffs and we'd be done. Why am I so interested in this alternative distribution, right? When with the hypothesis testing, the actual statistical testing we do only really looks at the null distribution. But I'll talk about a little bit later in this lecture why the alternative distribution is also important and interesting, right? Okay. Um, what else did I want to do? Okay, there's one more thing I want to show you about this, but I'll come back to this point later. Okay. So this was my code to kind of compute to bootstrap this Anova. All right. Any questions on this simple one-way Anova? Yeah, Yenu. Oh, yeah, you're totally right. This mean does nothing because this is a single statistic, right? Yes. Sorry about that. Please remove that mean. TAs, send me a message. Thank you. That was just there to make sure you're paying attention. Oh, you're paying a lot of attention. What's your next question? Yeah, okay, that's a great question. That's a really good question. So, you're talking about, yeah, first of all, remove this mean. We should not be looking at the mean. We should just look at the F statistic, okay? So your question is, why aren't we looking at the mean of all the alternative values of F that we computed, right? And, okay, the answer goes something like this. The F statistic that we compute using the classical Anova function that we have, that is actually the best estimate that we have of the F statistic. Bootstrapping it doesn't actually give us a better estimate of the overall F statistic. All right. So why are we bootstrapping? What bootstrapping does give us, however, is a better feel of the distribution of the null and the alternative values. All right. So we're bootstrapping for the distribution, not for the individual values. All right. So the average F statistic of the alternative values, they should be very close to this F statistic that we got through the classical means. And actually, do you remember a long time ago, I described that when we are resampling, I'm only doing 10,000, I'm bootstrapping 10,000 times, right? Ideally, I would bootstrap millions and millions of times. In fact, I would bootstrap as many times as there are permutations to this data. Ideally, that would be an exhaustive bootstrap. If I bootstrapped every possible combination of this data, I would get a very accurate bootstrap actually, but that number would be exceedingly large, in the millions or billions or more. All right. And because I can't bootstrap that much, I'm doing only 10,000 bootstraps. However, had I bootstrapped exhaustively every single possible combination of bootstrap that's feasible, if I had bootstrapped billions and billions of times, then the average value of those alternative F's would be exactly the F value of the original sample. All right. But since I'm not bootstrapping that many times, the mean is actually, the mean of these alternatives is actually not a correct, it'll be slightly, very slightly off. All right. So the original F value is the best estimates that you can possibly get. All right. So once again, the reason for bootstrapping is not because we don't trust the F statistic, it's the distributions that will no longer look really purely F if the data is skewed in a particular way. All right. Both the null distribution and the alternative distribution could look a little bit different if our data, for example, in Anova, doesn't have a normal distribution to begin with. All right. So bootstrapping is for the distributions, is not for the actual value of F. All right. So yes, do use the original F statistic, but when you're then asking, does it fall into a certain distribution or not? That's when you can use the bootstrap distributions. All right, they're probably more accurate. They're probably more accurate if the assumptions of Anova are not met. If the assumptions of Anova are met, just do classical Anova, no problem. All right, cool. And yes, here I am using the quantile function to get the 95 and 99% quantiles of the null distribution. All right, any questions on that? You're okay with this so far? So that was a very simple ANOVA. I want to show you a slightly more typical type of ANOVA result because it'll allow me to introduce something that we'll come back to later this semester. All right. So let's take a look at a completely different scenario. All right. Let's take a little stretch break. Okay. 30 seconds. Just stretch out. Forget the homework for a little bit. All right. Your nightmare is over. All right. Good. All right. I'm going to show you a different type of ANOVA, but it's still ANOVA. And let's take a look at what it's about. All right. So this is a scenario, and it's an imaginary scenario. This is not real data, okay? So please don't take the results of this too literally, and don't get disheartened or discouraged if the results say anything about you, all right? And don't get too encouraged if the results say anything about you. All right, so this is the story. So to improve students' performance on a standardized exam, so by standardized exam, I mean a kind of, does anybody know any particular standardized exams that you have to take to get into colleges? In Taiwan, for example, maybe you have to take this, or maybe this, every time you apply for a school, you have to maybe come in and take an exam to kind of score yourself. But oftentimes there are exams that you can take that can be applied anywhere in the world. Anybody know one of these exams that can be applied anywhere in the world? SATs, right? SAT is an exam that you can take to apply to colleges around, universities around the world. Most universities, well, many universities will accept an SAT score as some kind of something, all right? Um, so imagine something like the SAT. This particular story is about something called the GMAT, which is a standardized exam to get into business schools. We're in a business school. I thought I'll use a business school example. All right. So to improve students' performance on a standardized exam, a cram school in Taiwan is considering offering 3 different preparation programs to prepare to take this exam. All right. The preparation programs have different length and intensity. In particular, this school is trying to think whether it should, how to prepare students. One option is not to have an intensive preparation program, but just have a 3-hour review of GMAT and what it looks like, and just tell students how they can prepare themselves for it. So that's one thing the cram school is considering, just a 3-hour program, just to give students a little bit of preparation. Okay. Alternatively, they can have a full day program. So students can come in for one day. They can try a few different questions out, and they can have, like, a little bit longer time to absorb all the material. All right. Alternatively, you can have an extensive 10-week course on preparing for this GMAT. Okay. This is just an imaginary example. So the school is offering 3 types of preparation programs. All right. The outcome variable we're interested in here is the scores. So these values you're seeing here are the actual scores that students are getting on practice exams. All right. So in the school, they're at the end of each of these 3 programs, they're doing some practice scores, so that practice exams, so that they can get some scores to see how they perform. All right. Now, the school is also interested in how these programs will affect different types of students. So one more thing they're doing is that they're asking students to provide their school grades, so they can kind of categorize these students into 3 types: outstanding students who have very high school grades, average students who have average school grades, and students who are maybe below average, they have below average school grades. Okay. So um, so there is actually 2 factors at play. One is which type of preparation program you're using, all right? And the other factor that this cram school is taking a look at is what is the school performance, the regular school performance of these students. Are they average students, outstanding students, or below average students? All right. And so now here you're seeing the scores of about 18 different students who have done these programs. And what you will notice is that for each combination, like, so for example, average students doing the 3-hour review, we have 2 practice scores. All right. So essentially, we asked, perhaps 2 different students who are both average to do the 3-hour review. And similarly, we asked 2 students who are outstanding to do the 3-hour review, etc. So we have what is called replications. For each combination of factor A and factor B, where factor A is a preparation program and factor B is the ability, for each combination, we're doing 2 replications. We're making sure there's at least 2 students who try each one. All right. This kind of design of study is often called a factorial experiment design. it's characterized by two things. One is there's more than one factor that the experimenter is interested in. In this case, we're interested in the preparation program, which we call factor A. And the second thing is we're interested in students' ability, which we're calling factor B. Okay. And to be able to extract enough information about how A and B how these two things influence the outcome together, we have replications where every combination of factor A and factor B is replicated at least once. Okay, meaning that we have at least two values for each combination. All right. I'm not going to go too much into this. Maybe a design of experiments class will talk about factorial designs a little bit more, but this is just a rough idea of what a factorial design looks like. All right. There are some things about a factorial design that we'll come back later in the semester and talk about. So I just want to kind of get you a little used to it right now. But I'm thinking for the most part, you've seen a factorial design somewhere before in a stats class. Okay. All right. Any questions about how this experiment has been set up? Any criticisms about how this experiment has been set up? Any criticisms of the assumptions the experimenters are making in this experiment? Anything that makes you feel uncomfortable about it? Nothing? You're totally okay with everything? And I'm not even asking you statistically, are you uncomfortable with it? I'm just asking you conceptually, is there something you disagree with, or you feel, I don't agree about this or that? You're totally okay with everything? Wow, very easy to please. Great. Well, I'm not happy, but I'll explain why later. So this whole setup can also be analyzed using Anova, all right? And the Anova setup for it looks something like this. It looks a little bit more complicated, but let me just kind of explain to you what's going on here. In this Anova, like we did last time, we're going to compute some variability, degrees of freedom. We're going to divide the two to get a variance, and then we're going to compute some F statistics, okay? So let's take a look at what we're doing here. So in this Anova, we're going to look at first at factor A. Okay, factor A is these three separate programs. So this row of this row of computations, if I can highlight it, can I highlight it? Yes, I can. Great. This row of computations is basically looking at the three different levels of factor A. Okay, it's looking at how the 3-hour review is different from the 1-day program and the 10-week course. All right. And the way that is doing that is it's taking the data that's within these cells, okay, and it's taking the average of, let's say, this row of, oh, I cannot do it that way. You see this yellow row? It's taking the average of this yellow row, okay, and comparing it to the average of the whole data set. The whole data set is these 18 numbers, 9 times 2, these 18 numbers in these 9 cells, okay? So it's comparing the mean of the 1-day program to the mean of the whole data, all right? And that's just one time through this sum. The sum is also looking at the mean of the 3-hour review versus the whole data and the 10-week course versus the whole data, all right? So essentially, this sum of squares is telling us what is the variability between these three preparation programs, okay? What is the variability? And again, remember, variability means the sum of squares, all right? So this expression is the sum of squares here, okay? The variability. The number of programs we have, 3 minus 1 is the degrees of freedom. If we divide the variability by the degrees of freedom, we're going to get the variance of factor A. This tells us what is the variance of this data that is due to this 3 different programs? There's other explanations for this variance, but one way to explain the variance is the variance between these 3 programs. All right, this 3-hour review, this 1-day program, and this 10-week course. So that's what this row of this ANOVA is doing. All right. So once again, the sum of squares is looking at each row one at a time, okay, and computing the difference of this row of numbers from the total set of numbers. And it's summing it row by row. And that gives us the variability of factor A, the preparation programs, divided by degrees of freedom, and we get the variance. The mean square means the variance of this data due to factor A. All right. Let me actually run this data set and to kind of help motivate what it's doing. So I'm going to load this GMAT data. All right. I'm going to set up a simple using the AOV function. I'm going to just set up this story where I'm asking how does a score depend on ability and the program that they did. All right. And check the summary out. All right. So you will see here that what was factor A? Factor A was the preparation program, right? So the sum squares of the preparation program is this number. And if I divide by the degrees of freedom, then the variance is this, 3,000, all right? This variance tells me what is the variance of this whole data that is due to me having 3 separate programs, all right? I could also ask, how is the variance of all this data, all these 18 numbers, how is the variance explained by factor B? To do that, I would do something similar to what I did before, but this time I would go column by column, all right? So for example, I would take the average of this column and subtract it from the average of all the data here. That would give me, oh, excuse me, this should be SSB, by the way. TAs, can you just write SSB? All right, so, and that's this expression right here, squared, okay? Is 1 column minus the grand mean squared, all right? If I sum this if I sum for the 3 columns, the difference of each column's mean from the grand mean, that gives me the variability of factor B, the ability. And if I go here, I see the variability of the ability. You notice it's quite a bit different than the variability of the program. All right. So it makes a difference whether I'm taking the average of the rows and subtracting it from the total mean, or if I'm taking the average of the columns and subtracting it from the total mean. Doing it row-wise gives me the variability and the variance of factor A. Doing it column-wise gives me the variability and variance of factor B, okay, which is the ability. And once again, with the ability, with factor B as well, if I divide by its degrees of freedom, I'm going to get a variance. This is the variance of the data explained by the ability of students, their school ability before they did this program, all right? So this is kind of interesting. You're seeing 2 variances that are trying to explain this data. This is the variance of the data as it is explained by which cram school program the students are doing. This is the variance of the data explained by what is the prior ability of these students before they came to this cram school. All right. As you can see, the variance of the students on the test scores that they're getting, the practice scores that they're getting, is quite a bit bigger than the variance based by the program. This tells you right away that what score the students are getting on these practice exams is not so much determined by which program that they're doing, but rather what is their ability, their school ability before they even came into this program. All right, just because this variance is bigger than this variance. Right. So here, this is the variance of factor A, this is the variance of factor B. And I'm saying that the variance of factor B is much bigger than the variance of factor A, meaning the variance of their abilities is quite a bit bigger than the variance of which program they did. All right. So what's interesting about this is I'm using the same data to compute these two variances. I'm using the result that these students got on a practice exam at the end of whichever program they did. All right. The question now can be asked, okay, sure, this variance looks quite a bit bigger than this variance, but is it statistically bigger? All right, it's of course numerically bigger. This is 22,000 and this is 3,000. Can we do a statistical test? And the statistical test to compare two variances, as you will remember, is simply the F test. So, all right. So if I wanted, I could actually just divide these two variances by one another. However, in this ANOVA, I'm asking a slightly different question. I'm actually interested in knowing, is the variance of each of these factors actually any different from the error variance? All right. So let's take a look at how we might do that. So before I get to the error variance, I'm going to explain one more variance before I actually get to the error variance, okay? So I've explained how we get the variability and the variances of factor A and factor B. One more variance that I want to kind of explain is the interaction variance. And this is something we'll come back to later in the semester, but I want to just kind of introduce this to you now. Here, we're asking, what is the variance of this data that is explained not just by factor A and not just by factor B, but by the combination of A and B? All right, because we may have average students who are doing the 3-hour review, and their scores might be quite a bit different than the same average students who are doing the 10-week course, right? And similarly, we have outstanding students who are doing the 3-hour review, and we have outstanding students doing the 10-week course. It's possible that your performance at the end of these programs is not just which preparation program did you do, and it's not just how good a student are you, but it's possible that some programs are more effective for certain types of students than other programs. All right. For example, it's possible that the 10-week course is better for, let's say, average students. Maybe their performance improves more than, shall we say, for outstanding students. All right. And maybe possibly the 3-hour review is actually quite effective for the outstanding students, and they don't really need a 10-week course. All right. So one of the things we're interested in here is not just, is factor A important and is factor B important, but are there combinations of factor A and factor B that produce different results, right? These combinations is what we call an interaction, right? It's called interaction because you can think that factor A is interacting with factor B. They're working together in some way to produce different results, all right? And if we wish, we can compute this interaction as well. This interaction actually looks at the mean of each cell. All right, so it looks at the mean of each cell. For example, this cell, average students doing the 3-hour review. It looks at the mean of each cell minus the mean of the column, minus the mean of the row, minus the mean of the entire data. All right. And we do this cell by cell. So there's two sum expressions here because we're summing by rows and by columns. We're doing this cell, then this cell, then this cell, so on and so forth, all 9 cells. All right. If we sum all these up, we will get an interaction variability. The degrees of freedom now is actually a minus 1 times b minus 1. And if we divide the variability by the degrees of freedom, we get the interaction variance. So in this run, I don't have the interactions. If I want to introduce the interactions, I have to change my syntax, my code a little bit. All right. So here you'll notice I'm saying the score is dependent on the ability of students, the program that they have actually taken in the cram school, and the combination of the ability and the program. All right. This is what we call the interaction term. And now Anova will give us a sum squared for the interaction, which is very large, but the degrees of freedom is also quite large. Is twice the size of the degrees of freedom of the other two factors. And then the interaction variance, which is actually smaller than these. All right. Before we finish it up, we can compute what's also the variability and the variance of the error. This simply means what is the variability of this data? Okay, so we've computed the variability of this data in 3 separate ways. Factor A, factor B, the interaction of factor A and factor B. And what we can also do is we can compute the variability of the entire data set, which is going to be the variability of the entire data set is this. It's each and every single value that you see here. So like this value minus the grand mean, this value minus the grand mean, this value minus each of these differences squared. And this time there's 3 sum expressions because we're summing within a cell, across the rows, across the columns. All right. So this gives us the total variability. The error variability is going to be this total variability minus the variability of factor A, factor B, and the interaction. Right? So if you take the total variability and remove from it the variability explained by factor A, the variability explained by factor B, and the variability explained by the interaction, which I'm calling SSAB, that gives me the error variability. All right. The degrees of freedom of the error variability is this expression. Okay, it's the number of factor A, the number of levels of factor A, the number of levels of factor B, and the number of replications within each cell. All right, and if I divide the error variability by the error degrees of freedom, I get the error variance. Okay. One thing I explained last time, which is you'll notice here very clearly, is you will see that the variabilities add up. All right. So when I'm explaining the dispersion of this data set using variability, I can say that the total dispersion as explained by variability is the total variability is not written here, but the total variability is going to be the variability of factor A, the variability of factor B, the variability of the interaction, plus the error variability. R calls this residuals, and we'll see in a later week why we like to think of this as residuals, but this means error for now, okay? It means everything that is not factor A, not factor B, and not the interaction, all right? So this is the variability of the data that is not explained by A, B, or the interaction of A and B, all right? And it's got a much larger degrees of freedom, and this is the error variance, all right? You'll notice in this table in your notes that I am not computing a total variance here. for a couple of reasons. One is I don't need it, but the second thing is it doesn't help me because variances don't add up. If I add the variance of factor A, the variance of factor B, the interaction variance, the variance of the error, I am not going to get the variance of this raw data. All right, they simply do not add up. And the reason is because each of these terms is divided by a different denominator, so they simply cannot add up. However, variabilities do add up. So that's why you will often see in analyses, you'll see us using variabilities and variances, because variabilities have this really nice property that they add up, whereas variances do not. Okay. However, even though variances do not add up, they have this other nice property, which is when you divide a variance by the other variance, you end up with something that looks like an F distribution. And that has known properties that we can use to do F tests. All right. So in this simple example, one F statistic we can compute is if we are interested in asking, is factor A the preparation program, right? The school must be curious, does it make a difference to have these three different preparation programs? Or could I just use like anyone? I mean, does it really matter that do these three different programs make a difference? One way of answering that question is to do an F test where you compare the variance of the data as explained by factor A compared to the error variance. Remember again, the error variance here is the variance of the data that is not explained by factor A, factor B, or the interaction. It's all the other unexplained reasons for variance in this data. That's what the error variance is, okay? You can think of this error variance then as the variance of the data that is due to all the other things in the universe other than the preparation program, the ability of students, and the interaction of those two things. All right. So to ask, is the preparation program actually useful? We can do an F test where we just simply ask, is the variance of scores due to the preparation program, is it significantly different than the error variance, all the other explanations that are out there? All right. And this will give us an F statistic that R can then use to compute a p-value. So in this case, the F value, so we divide this, we divide this variance due to programs, this is factor A, by the error variance, gives us an F value of about 1.383, which kind of tells us the p-value of that is about 0.29. It tells us that this is not significant at 5%, is not 99% is not even significant at 5% or even 10%. So this tells us that perhaps which program they're using is not the important thing. All right. Whether they use the 3-hour program, the 1-day program, or the 10-week program is not what is producing significantly different scores. All right. On the other hand, the F test, where we take this F value, takes the factor B, which is the ability, and divides it by the residuals. And that gives us an F value. You can see it's roughly 10 times bigger. It gives us an F value of roughly 10. All right. The p-value here is very small, which suggests that actually the scores the students are getting at the end of their training is largely due to the ability that they had before they even came into these programs, before they even came into the cram school. So really, it's not the cram school that's making that big a difference. It's the pre-existing ability of the students. All right. So maybe this cram school should rethink how it's doing these programs because they're not really making much difference. All right. This is just an example. This is not to say anything bad about any cram school. All right. It's just an example. All right. And the last thing we can look at is this interaction. We can ask, well, maybe it wasn't factor A, the preparation. Maybe it wasn't factor B, the ability. Maybe it was something about the combination of factor A and factor B. Maybe students who were already outstanding, maybe they did better because of one of these preparation programs, but maybe they didn't really change because of the others. Well, we can test the interaction as well. We can take the variance of the interaction and just divide it by the error variance as well. All right. And the AOV function gives you that F test as well. This is simply the interaction variance divided by the error variance. And that gives us an F statistic that we can test. And that is also not significant at 1%, 10%, not even 20%, not even 30%, because its p-value is closer to 35%. All right. So in this case, maybe this cram school will realize, that its preparation programs are not that helpful. It's really the ability of the students coming into the program that's producing these scores. All right. So this is a simple demonstration. Oh, and I've got a little bit more to show on this. So here's the code for everything I just did: loading the data set, running analysis of variance. This analysis of variance is effectively a blocking design. I'm just comparing two factors to each other. With a full factorial design, when I have replications for each combination, I can add an interaction term. And this will give me an Anova table with an interaction row as well. Okay. So that's just a crash introduction to reintroduction, I hope, to factorial designs. I'm going to have a homework assignment where you'll have to do a factorial design. It's not that difficult. You just do this. You just have to run AOV. All right. The last thing I want to show you is what we call an interaction plot. And to me, this is often the interesting thing. All right. The interaction plot is really a visual understanding of this whole Anova with an interaction term. And let me first show you the code this way. In your notes, I've done it a slightly different way. Let me just do it. Let me first show it to you this way. Okay. So there's a command called interaction plot. And let me first visualize it, then I'll show you what it does. And then I'll come back to the syntax. So this is what we call the interaction plots. And what it shows me is this. It tells me, all right, so on the y-axis is the dependent variable. This is the practice exam score of the students. Okay, those 18 numbers in the original table. All right. In the x-axis is the 3 different preparation programs. They're maybe sorted in a weird way, but this is the 10-week program, the 1-day program, and the 3-hour program. All right. So actually, the shortest program is to the right. The second longest is in the middle. The longest program is on the left. Right. However, you'll notice that there are 3 different plots here. There's 3 different lines. The 3 different lines correspond to the average, outstanding, and the below average students. All right. So this picture is really showing me is a visualization of this factorial design, of this factorial Anova. All right. What it's showing me, for example, and I'm just going to try to help you interpret it a little bit, is that let's take the outstanding students. They are this solid line right here. It looks like their scores in the 10-week program and the 1-day program are almost identical, very high. But for the 3-hour program, they have considerably lower performance. Okay. If we look at the average students, they are this kind of dotted, small dashed line. Their scores after a 10-week course is almost identical with the outstanding students, right? It's quite a bit different for the 1-day program. And, well, both the outstanding and the average students are not performing all that excellently with the 3-hour program. With the below average students, none of the programs really seems to be helping them at all. All right. So we have two ways of analyzing this data. One is statistically through the use of F statistics and p-values, and the other is visually. All right. Statistically, what it's telling us is that the ability matters a lot. The program doesn't matter that much, and the interaction of the program and ability is not that important either. Visually, and I've got the visualization here as well, we're seeing a similar story. It seems that the ability matters a lot, but particularly it's the below average students who were not helping with our program at all. And actually our program seems to be, and the students who come in with average or outstanding abilities are the ones who seem to be doing well with a high level of training, but their performance also drops as the training period is shorter and shorter. All right. All right. I'll say a little bit more about factorial designs next week in class. After you've done a simple homework assignment, it's not going to be very difficult, where you're just kind of looking at some scenario like this. But rather than this fictional data, I'll give you some real data from a real scientific study that you can use to do something like this, okay? So don't feel pressured to understand this all today. I hope this is a recap to a certain degree. But for those of you who've totally forgotten factorial designs, I'd like you to just play with it on an assignment, and we'll talk about it briefly at the beginning of next week's lecture, okay? But I want you to keep in mind this one thing, that there are two ways of looking at this problem. One is statistically and one is visually, all right? And we'll ask ourselves a little bit about how do these things correspond, which is important, which is not important, right? Any questions so far on this? All right. You may have more questions after you actually try to play with it on a data set by yourself. Then you may realize, yeah, I didn't understand this, or I didn't understand that. Or you might be able to verbalize it at least next week in class, right? So as always, oh yeah, there's one more thing I want to mention about the syntax, all right? What I want to mention about the syntax is that you will see that in my R code here, oops, excuse me. In my R code here, there is this excuse me. Hold on. Sorry. In my R code here, in this interaction plot, it looks a little ugly because every variable I'm looking at. So what are the variables I'm looking at? The x-axis is called the x factor because it's one of the factors in my Anova. And I have to say GMAT data dollar program. Trace factor and response. So response is the y variable. That's the GMAT data score. The trace factor is the GMAT data's ability variable. Okay. It may look a little ugly because I have to keep saying GMAT data, GMAT data, GMAT data. Whenever you're writing some code and you keep finding yourself typing the same thing again and again, like GMAT data dollar this, GMAT data dollar that, there's a little bit of a shortcut to make the code a little bit cleaner, maybe. Depends on whether you think it's cleaner. Here's the interaction plot command again. It's the same function as up here. All right, it's just right down here. But this time you'll notice I don't have to say GMAT data, GMAT data, GMAT data. I can just say program ability score. And the reason I'm able to do that is because I'm wrapping this function in a larger function called width. And the width function says, everything I'm about to do is with this data called GMAT data. So within the width function, which is this whole thing, within this width function, the second thing I give it, I can just give it the command that I normally want to give it, but I don't have to specify this data frame name anymore, all right? If it cannot find a variable called program, it will look in this data frame for me, all right? So that's. All right. So that's why you'll see my data here my code here looks like this. All right. Okay. All right. That's all I want to mention about factorial designs. We'll play with it a little bit for homework. We'll come back, but let's take a little break. After the break, I want to come back and talk about something I have not talked about in class. Some of you might be surprised, which is about these p-values, and go back to talking about how come I don't seem to be that insistent about 95%, 99%, and all this stuff. Should we be a little bit more strict about it? Okay. So let's take a little break. We'll come back and talk about this. All right. Thank you.